Have you ever just stared at your smartphone screen while you're away from home?
Oh, yeah. Like when you're out running errands.
Right, exactly.
Yeah.
Maybe you're navigating a new part of town or you're sitting in a crowded restaurant and you see that terrifying blinking 1% battery warning.
It's the worst. You instantly start doing the mental math.
Yeah, you know that distinct sinking feeling. Your heart rate ticks up just a fraction of a beat.
Right.
You start debating whether you need to, send that one critical text message before the screen goes completely black.
Because once it's dead, it severs your entire connection to the world.
Exactly.
Yeah.
Now, I want you to take that exact same feeling of modern technological panic, but multiply the states by an order of magnitude.
Oh, wow. Okay.
Imagine you aren't just holding a dead phone. Imagine you are sitting inside a dead 4,000-pound electric vehicle.
That's a completely different level of stress.
Right. You are stranded on the side of a roaring highway. Semi-trucks are blowing past your door at 70 miles an hour, rattling the glass. And your dashboard has just gone completely dark. The climate control stops. The screens go black. You are entirely out of juice, and you are entirely physically stuck.
It represents this incredibly distinct, uniquely modern kind of helplessness.
Yeah.
I mean, if you're driving a traditional internal combustion engine and you run out of gas, the solution is highly analog and relatively simple, you know?
Yeah, you walk to the nearest exit.
Exactly. You buy a little plastic jug, you fill it with a gallon of unleaded, and you walk back. You carry the fuel to the machine.
Right.
But you cannot carry a bucket of electricity down the shoulder of the interstate.
No, you definitely can't.
You're dealing with an energy system that requires specialized, high-voltage delivery mechanisms, which honestly completely rewrites the rules of what it means to be stranded.
And that specific scenario, that incredibly modern nightmare, is the actual mission of today's deep dive.
It's a great topic.
We are going to explore the hidden, rapidly evolving logistics of the EV revolution. We're really looking at the massive logistical tail that follows these vehicles.
Right, the stuff people don't think about.
Exactly. And we are going to do it by analyzing the operational blueprint of one specific, highly revealing business, Sacramento Mobile EV Charging.
This blueprint is fascinating, by the way.
It really is. We have complete access to their service details, their hardware specifications, their routing logistics.
Their pricing models, too.
Yeah, their a la carte pricing and their long-term business strategy.
You know, the broader context to keep in mind here is that the most fascinating aspect of transitioning a society to electric vehicles isn't the sheet metal or like the acceleration times.
Right, the cars themselves are sleek.
Yeah, they capture all the marketing attention. But the true limiting factor of any technological revolution is the invisible support infrastructure.
The stuff behind the scenes.
Exactly. The infrastructure required to keep the hardware functional when the primary systems fail. We're really looking at the emergency safety net for a new era of transportation.
Okay, let's unpack this. Because diving into the operational manual of this Sacramento-based company isn't just about reviewing a local roadside assistance crew.
No, not at all.
It is a real-time window into how an entire secondary industry is actively scrambling to patch the vulnerabilities of a massive technological shift.
Yeah.
But to understand why a mobile charging business even needs to exist, we first have to examine the deeply flawed legacy system that it is actively trying to replace.
Right, the old way of doing things. Because the default response to a highway breakdown has remained largely unchanged for a century.
You just call a tow truck.
Exactly. The moment a vehicle stops moving, the immediate instinct is to dispatch a tow truck. But applying that century-old solution to a modern electric vehicle creates a cascade of entirely new, highly complex problems.
The operational blueprint we are looking at actually refers to this default response as the towing trap.
That's a perfect name for it, honestly.
It really frames traditional towing not as a solution, but as a compounding disaster for an EV owner. If you follow the old way and call a flatbed, the financial reality gets grim incredibly fast.
Oh, the numbers are brutal.
Yeah, just getting towed to a dealership or a specialized charging plaza runs anywhere from $200 to $400 just for the transit.
Just removing the car.
Exactly. Then The dealership or service center assesses a charging fee, which adds another $50 to $150.
Right.
So before your car even has enough range to drive home, the baseline financial damage is between $300 and $600.
And that figure completely ignores the secondary costs,
Like renting a car.
Yeah, renting a car for the day, or taking an Uber 30 miles back to your house while your vehicle just sits locked behind a chain link fence at a dealer lot.
It's insane. But the financial extraction is only one dimension of this towing trap.
Right. The human cost measured in lost time is arguably far more punishing.
Oh, absolutely.
I mean, the standard traditional towing process results in a loss of 4 to 8 hours. A stranded driver might wait 1 to 3 hours simply for the flatbed to arrive.
Because tow trucks prioritize severe accidents, right?
Exactly. Traditional towing operates on a triage system based on mechanical severity, not battery levels. If your battery is just dead, you're at the back of the line.
Wow, that makes sense.
Then you have to factor in the loading time, the slow transit through highway traffic, and the administrative bottleneck of checking the vehicle into a dealership queue.
And then the actual time spent waiting for the car to accept a charge.
Exactly. A single miscalculation in range effectively deletes an entire workday, or completely ruins a weekend trip.
What's fascinating here is the fundamental paradigm shift in the anatomy of breakdown. Historically, when a gas-powered car died on the highway, it meant structural mechanical failure.
Right, like a timing belt snapped.
Yeah, or the alternator seized, or the radiator cracked and dumped coolant everywhere. The vehicle physically required a garage.
It needed hydraulic lift, pneumatic tools, a mechanic.
Exactly. Moving the heavy machine to a specialized facility was the only logical remedy. But a dead EV represents something entirely different. It's merely an energy failure.
The vehicle itself is mechanically pristine.
Right. The motors are fine, the axles are fine, the computers are perfectly operational. It just lacks the electrons to boot up.
It's an empty cup, basically.
Yeah. And the operational strategy of this Sacramento business zeroes in on this distinction perfectly. As they say in the manual, it's a battery problem, not a tow trap problem.
That distinction completely invalidates the old model. Moving the vehicle is a massive overreaction to the actual deficit.
My understanding of the EV chassis makes the idea of traditional towing seem even more absurd.
Oh, it really is.
I mean, towing a gas car is like picking up a heavy backpack by the reinforced top handle. The weight is concentrated in the engine block, and the chassis is designed to be pulled from specific structural points.
Right.
But towing an EV using a traditional winch feels like trying to drag a massive, incredibly fragile flat-screen TV face down across the pavement.
That's a horrifying analogy, but very accurate.
The marketing materials for this mobile service lean heavily into this. They specifically warn about the risk of flatbed damage.
Yeah.
But I want to theorize on this for a second.
Sure, go ahead.
We know the batteries are built into the floor to maintain a low center of gravity. But does winching an EV onto a flatbed genuinely present a higher physical risk? Or is this just like a clever fear-based marketing tactic to steer people away from calling AAA?
No, the risk is entirely real, and it's deeply rooted in the geometry and the physics of the vehicle's architecture.
Okay, break that down for me.
Well, the skateboard design you're referring to means the heaviest, most sensitive, and most expensive component of the car. The lithium-ion battery pack spans almost the entire underbelly of the vehicle.
Right.
It's sitting just inches above the asphalt. Now, it is separated from the road by a protective shield, but that shield is not designed to bear the structural stress of being dragged at a weird angle.
Oh, I see.
When a tow operator winches a car up the steep steel ramp of a flatbed, the angle of approach changes drastically. If the breakover angle is miscalculated, the apex of that steel ramp can literally scrape or even puncture the battery enclosure.
Which is catastrophic. A compromised battery enclosure isn't just a dent, it's a thermal runaway risk.
Precisely. It introduces moisture and oxygen to the cells, turning a simple roadside inconvenience into a total loss and a severe fire hazard.
Wow.
And furthermore, the drivetrain of an EV complicates the physical movement of the car. Many modern electric vehicles, particularly when the low-voltage 12-volt battery also dies, cannot be easily shifted into a true free-rolling neutral.
Because the parking brake is electronic, right? And the motors are permanently engaged with the wheels.
Yes, they use permanent magnet synchronous motors or induction motors. If a tow operator forcefully drags an EV while the wheels are locked or the motor is engaged, the physical turning of the wheels forces the electric motor to act as a generator.
Wait, it generates power while being dragged.
Exactly. It creates back electromotive force back EMF. This pushes unmanaged, unregulated electrical current backward into the vehicle's dormant inverters and control units.
And unmanaged current is the absolute enemy of sensitive electronics.
Exactly. Dragging the car can literally fry the propulsion systems. So the risk of catastrophic damage during a tow is statistically much higher than with a traditional internal combustion vehicle.
Okay, so if dragging the vehicle to the energy source is structurally dangerous, wildly expensive, and destroys half your day, the only logical remaining option is to reverse the logistics.
You have to bring the energy source directly to the vehicle.
Right. But that introduces a massive engineering hurdle. We aren't talking about tossing a 2-gallon plastic gas can into the back of a pickup truck.
No, not at all.
You have to safely transport highly dense, high-voltage electric power down the interstate, stabilize it on a slanted gravel shoulder, and pump it into a highly sophisticated computer on wheels.
The logistical pivot from moving metal to moving energy requires highly specialized hardware.
Yeah.
The equipment they're deploying has to bridge the gap between heavy industrial power generation and delicate consumer electronics.
Here's where it gets really interesting. Let's look at the actual machine Sacramento Mobile EV Charging uses to solve this physics problem.
The hardware is fascinating.
They utilize a professional-grade unit called the EV Hero. When you look at the physical dimensions, it's incredibly compact for what it does.
Yeah, it's basically a cube.
Exactly. It's a ruggedized cube, 29 inches on all sides. It weighs just over 200 pounds, and it's designed with integrated mobility. It has built-in wheels and a heavy-duty handle, so the single technician can maneuver it around the debris and uneven terrain of a highway shoulder.
Right, because highway shoulders are rarely flat and clean.
But the power source is the detail that completely stops you in your tracks.
Yeah, this is the irony of the whole operation.
This machine, designed specifically to rescue zero-emission electric vehicles, runs on a 6.1-gallon combustion gas tank.
It really highlights a profound paradox in the current energy transition.
It seems beyond paradoxical, honestly. It feels almost absurd on its face. I can imagine EV purists losing their minds watching a technician pour unleaded gasoline into a generator to charge their $90,000 Lucid Air.
I'm sure it happens.
Why on earth wouldn't a mobile EV charging company use a massive lithium-ion battery bank to charge the stranded EV? Why rely on old-school combustion?
Because when you are operating in the realm of emergency roadside triage, the laws of physics and the demands of pragmatism will violently override any environmental idealism.
That makes sense.
You have to analyze the primary objective. The objective is not to save the environment in that specific moment.
Right. The objective is to get the person off the highway.
Exactly. The goal is to extract a stranded human being and a 2-ton road hazard from a high-velocity danger zone as rapidly as possible. To accomplish that, the rescue vehicle requires an energy source that is incredibly dense, highly portable, and instantly replenishable.
And gasoline still holds the crown for energy density.
By a massive margin. If we look at the specific energy of the fuels, gasoline contains roughly 46 megajoules of energy per kilogram.
Okay.
A state-of-the-art lithium-ion battery pack might contain 0.5 to 1 megajoule per kilogram. Gasoline is nearly 50 times more energy dense by weight.
50 times?
Yeah.
Yeah.
If this company attempted to build a mobile charging unit capable of performing 10 consecutive rescues using only auxiliary batteries, a battery charging a battery, the physics become unmanageable.
What would that even look like?
To output 16 kilowatts of power continuously for hours, the rescue truck would need to carry an 80 to 100 kilowatt-hour battery pack. That equipment would weigh over 1,000 pounds, take up the entire cargo bay of the truck, and cost tens of thousands of dollars.
That's a huge barrier to entry for the business.
And crucially, once depleted, the rescue vehicle would have to return to a base station and sit completely idle for 6 hours to recharge.
Which would completely destroy their dispatch availability.
Exactly. But with a gas generator, the technician simply pulls into a Chevron station, spends 3 minutes and $20 filling that 6.1-gallon tank, and the rescue vehicle is immediately back online, ready for the next dispatch.
So the operational uptime approaches 100%.
Yes. The gasoline is merely a highly efficient liquid transmission mechanism to get the necessary kilowatt hours to the side of the road.
Okay, let's dig deeper into the actual output specs of this EV Hero unit. Because it's clearly not just a loud, vibrating construction generator you pick up at a big box hardware store.
No, absolutely not.
It features an electric start operated via wireless remote, meaning the technician can manage the power flow while managing traffic safety.
Which is vital.
And the noise level is rated at 64 decibels from 23 feet away, which is surprisingly quiet, roughly the volume of a normal conversation.
Right, and that's critical when you are trying to communicate with a stressed driver on a loud highway.
It outputs 9 kilowatts of continuous power and can peak at 16 kilowatts. That translates to true level 2 charging speeds delivered through a heavy-duty 25-foot cord.
That 25-foot measurement isn't an accident, by the way. It's a highly intentional safety feature.
How so?
It allows the rescue technician to position their dispatch truck and the generator at a significant distance from the stranded vehicle, or they can position it at an awkward blocking angle to act as a physical steel buffer against oncoming traffic.
Oh, like a shield, while still easily reaching the EV's charging port.
Exactly.
Compatibility is also universal. The unit utilizes the industry standard SAE JSIMN 72 connector, but they explicitly carry Tesla adapters as well.
They have to, given Tesla's market share.
Yeah, the operational manual specifically lists readiness for Tesla, Rivian, Lucid, Ford, Chevy, Hyundai, Kia, and Nissan. They also integrate localized safety protocols like a carbon monoxide auto shutoff and mandate that the service is actively supervised by a licensed technician for the entire duration of the charge.
The supervision is key.
But the most critical engineering spec in their entire blueprint revolves around the quality of the electricity itself. They heavily emphasize that the unit provides ultra-clean power, maintaining something called a THD of less than 3%.
This is the most important technical detail in the entire document.
Really? My understanding is that EVs essentially act as massive surge protectors. They will completely reject grid instability. If you feed an EV jagged, fluctuating power, its onboard inverter will just shut the gate to protect the battery chemistry. Is that right?
Your understanding is spot on. And this metric, total harmonic distortion, or THD, is the dividing line between a professional roadside service and a catastrophic amateur mistake.
So what exactly is THD?
To understand why THD matters, we have to look at how an EV actually consumes electricity. The battery pack stores energy as direct current, or DC.
Okay, DC power.
But the generator on the side of the road, just like the power grid at your house, provides alternating current, or AC. The vehicle has a complex piece of hardware called an onboard charger, or OBC, which takes that AC power and rectifies it into DC power to feed the battery.
And that onboard charger is packed with sensitive microcontrollers, capacitors, and silicon carbide transistors, right?
Precisely. When power comes from a highly regulated municipal grid, it arrives in a smooth, perfectly symmetrical sine wave. The voltage rises and falls in a predictable, stable rhythm. That is what we call clean power.
And the EV's onboard charger expects this smooth rhythm.
Yes. However, a cheap, low-quality gas generator produces a very chaotic electrical output. As the small combustion engine revs up and down under load, the electrical wave it produces becomes jagged, spiked, and distorted.
Oh, I see.
It creates harmonic frequencies that ride on top of the main power wave. This is total harmonic distortion.
So what physically happens inside the car if a tow truck driver unloads a cheap 20% THD generator from their truck and plugs it into a Rivian?
The vehicle's power factor correction circuits will immediately detect those jagged voltage spikes. In the best-case scenario, the EV software will identify the power as dirty and instantly terminate the charging session.
It just refuses to accept the charge.
Right. It throws an error code on the dashboard and refuses to accept a single electron. The car protects itself, but you remain stranded.
In the worst-case scenario.
In the worst-case scenario, if the software fails to catch it quickly enough, those jagged voltage spikes will force the internal capacitors of the onboard charger to rapidly charge and discharge out of rhythm.
That sounds bad.
It generates massive amounts of excess parasitic heat. Within seconds, you can literally melt the silicon components of the AC to DC converter.
Oh, wow.
By engineering the EV Road Hero to maintain a THD of less than 3%, they are forcing a small combustion engine to perfectly mimic the stable, ultra-clean sine wave of a multi-billion-dollar municipal power grid.
That is a brilliant engineering workaround. They are utilizing century-old combustion mechanics to synthesize flawless grid-quality power for the most advanced vehicles on the planet.
It's the only way to safely interface with the vehicle's rolling supercomputers.
But, generating the power is really only half the battle. The other half is time. How does this clean power actually translate to miles on the road for the person gripping the steering wheel, sweating about getting to their destination?
Time is everything in this business.
This brings us to the underlying mathematics of time, distance, and geographic dispatch logistics.
The math here defines their entire value proposition. If the math doesn't work for the consumer schedule, the whole business model collapses.
The operational blueprint lays out their central rescue ratio very clearly. The Road Hero hardware adds approximately 5 miles of driving range every 11 to 12 minutes of continuous charging. Let's run a hypothetical highway scenario. If you are stranded on the side of Interstate 80 and your navigation system says the absolute nearest fast charging station is 15 miles away, you are looking at sitting on the shoulder, tethered to this roaring cube for roughly 36 minutes, just to acquire the minimum battery percentage required to leave.
It sounds like a long time.
36 minutes feels like an eternity when cars are flying past you.
Yeah.
How does a company manage the psychology of a customer who expects an instant fix?
They manage it through radical, almost brutal transparency. The operational manual explicitly tackles this psychological friction.
What do they say?
They state clearly, charging speed depends on vehicle type, battery state, weather, and other factors. Our realistic estimates help you plan your rescue, not mislead you with inflated claims.
Interesting.
What they're doing is establishing a baseline of truth to counteract panic, because panic thrives on uncertainty.
Yeah, that makes total sense.
When a driver is stranded, their adrenaline is spiking. If a dispatcher promises, we'll have you fully charged and on the road in 10 minutes, the driver will mentally anchor to that 10-minute mark.
Right, and when minute 15 rolls around and the car still can't move, that panic turns into intense anger directed at the service provider.
Exactly. By setting a scientifically grounded, highly conservative expectation 5 miles every 12 minutes, they reset the driver's internal clock.
And while 36 minutes sounds long in a vacuum, you have to weigh it against the alternative we discussed earlier.
Precisely. 36 minutes of charging is vastly superior to waiting 3 hours for a flatbed tow truck to even arrive.
But to even begin that 36-minute charging session, the technician has to physically navigate to your GPS coordinates, and their dispatch grid is staggeringly large.
It's massive.
The blueprint notes they dispatch centrally out of Folsom, California, but they cover a 45-mile operational radius. They explicitly name 18 distinct cities in their service area.
That's a huge chunk of Northern California.
We are talking about the dense urban grid of downtown Sacramento, sprawling suburban environments like Roseville, Elk Grove, and Citrus Heights, university towns like Davis, and then pushing far out into areas like Auburn and Placerville.
Right.
Across that massive, varied map, they offer a strict 30 to 45-minute response time guarantee, claiming an average arrival of 35 minutes.
Which is incredibly fast.
Getting across Sacramento in 35 minutes on a good day is hard enough. How do they maintain that average across a 45-mile radius?
Maintaining that response time requires incredibly sophisticated dynamic geographic routing.
How so?
Well, a 45-mile radius extending from Folsom covers drastically different topographies. You have flat, stop-and-go gridlock in the urban centers, but as you move east toward Placerville and Auburn in El Dorado and Placer counties, you are ascending into the foothills of the Sierra Nevada mountains.
You're dealing with winding two-lane roads and significant elevation gains.
Exactly, which, ironically, is exactly where EV range anxiety becomes a critical failure.
Oh, because climbing a 6% grade into the foothills requires massive energy output. Drivers watch their battery percentage absolutely plummet in real time.
The elevation profile practically guarantees more stranded drivers in those specific corridors. To promise a 30-minute arrival across that map means they are not operating a static fleet.
They can't just have one truck sitting in a garage in Folsom waiting for the phone to ring.
No, that would result in 90-minute response times to the outer edges. This implies they are using predictive staging.
Like an ambulance service.
Very similar. They likely analyze historical breakdown data, traffic patterns, and weather conditions to dynamically position their dispatch vehicles.
Oh, that's smart.
They might orbit one technician along the Highway 50 corridor toward Placerville to catch the elevation drain victims, while another vehicle stages near the I-80 junction in Sacramento to cover the urban sprawl.
It requires a constant algorithmic game of geographical chess to keep that 35-minute average intact.
And the operational overhead to maintain that kind of predictive staging, keeping technicians idle but ready in strategic zones, has to be immense.
Which leads directly to the question of consumer cost. What is the actual financial price of this specialized convenience? Let's break down the economics of a la carte, emergency roadside services.
The pricing model reveals a fascinating approach to consumer psychology.
It really does. It's an approach that stands in stark opposition to the legacy towing model, which relies almost entirely on information asymmetry.
Right, because when you call a tow truck, you rarely get a fixed
It's
price.
a total black box. The dispatcher gives you a vague quote based on mileage, hook fees, and yard fees, and you don't know the final damage until the car's unhooked.
The Sacramento Mobile EV charging blueprint attacks that exact pain point.
They heavily emphasize flat, upfront pricing, approved before charging begins, no surprises, no hidden fees.
Which is very comforting when you're stranded.
They segment their rescues into 3 specific tiers, based purely on the time the vehicle spends tethered to the EV Road Hero. First, we have the Quick Rescue.
Okay, what's that run?
This is priced at $149, and it provides up to 15 minutes of level 2 charging. This is essentially an emergency triage boost, just enough energy to limp the vehicle to the absolute nearest highway exit or local charger.
Makes sense.
Next is the Standard Rescue. The manual marks this with a star as the most popular choice. It costs $249 and delivers up to 30 minutes of charging.
Okay.
Finally, for $349, they offer the Extended Rescue, providing up to 45 minutes of charging, intended for scenarios where the battery is completely zeroed out in a highly remote location. Now I have to step in and push back on these numbers.
Let's hear the critique.
Let's analyze that most popular tier. You are charging the customer $249 for 30 minutes of charge. Based on their own mathematical formula, 30 minutes of charging yields roughly 12 to 15 miles of driving range.
Right.
If you break that down, the customer is paying roughly $16 for every single mile of range they receive. Considering that the actual grid electricity required to drive 15 miles costs maybe 50 cents, charging $250 feels incredibly exploitative at first glance.
I can see why you'd say that.
It feels like price gouging a stranded motorist.
This brings us to a foundational concept in behavioral economics: the subjective theory of value. We have to clearly define what the customer is actually purchasing in that high-stress moment.
Well, they certainly aren't buying 50 cents worth of alternating current.
No, the electricity is effectively free. It is merely the byproduct of the transaction. What the customer is purchasing is logistical intervention. They are buying the immediate recovery of their schedule and the complete avoidance of the towing trap.
Okay, I see where you're going.
It is easy to view $249 for 15 miles as absurd when you evaluate it from the comfort of your living room. But the pricing is completely contextual.
Context is everything.
You are not choosing between a $259 emergency charge and a $10 top-up at a local supercharger. That $10 supercharger is physically inaccessible to you.
Right. Your actual real-world choice is between paying $249 to lose 45 minutes of your day versus calling a tow truck.
Exactly. Calling a tow truck, paying a $400 flatbed fee, paying a $100 dealership drop fee, risking structural damage to your vehicle's undercarriage, and losing your entire Tuesday.
Wow, when you put it like that.
When framed against the grim reality of the alternative, that $249 isn't price gouging. It is a highly calculated emergency tax that preserves your day. It is the ultimate premium for time saved.
And when you're sitting on the shoulder of a highway, time and safety are the only currencies that matter.
Precisely.
But looking closely at the granular details of their pricing structure, there are several fascinating add-on fees that illustrate how tightly they have to protect their operational margins.
Let's hear them.
If a breakdown occurs between 6 p.m. and 6 a.m., they apply a $50 after-hours fee. If you happen to be stranded outside their massive 45-mile primary radius, they don't refuse service, but they add a surcharge of $3 to $5 per mile.
That's standard for logistics.
However, the fee that really caught my eye is listed as a restart or replug fee of $50.
Yes.
Why would company penalize a customer just for unplugging the cable?
That specific fee is a brilliant operational safeguard against human error.
How so?
The charging protocol between an EV and a power source isn't like plugging in a toaster. It requires a complex digital handshake.
Right.
The EV Road Hero and the vehicle's onboard computers have to establish a pilot signal, verify the safety of the connection, negotiate the voltage, and continuously monitor the flow of power.
It's a delicate software negotiation.
Highly delicate. Often, a stressed, impatient driver might decide to abort the charge early, or they might open the car door and trigger a software interrupt that pauses the charging session.
Oh, just opening the door can interrupt it.
Yes, depending on the vehicle. And if the session is broken, the equipment doesn't just resume instantly. The technician has to power down the generator, clear the error codes on the vehicle, reseat the heavy charging cable, and reinitiate the entire digital handshake.
That sounds tedious.
Every minute the technician spends troubleshooting a user-created error is a minute they are not traveling to the next stranded customer. The $50 restart fee is a psychological deterrent.
It essentially tells the customer, once we start the machine, step away from the vehicle and let the hardware do its job.
Exactly. It protects the dispatch schedule.
But to counterbalance the anxiety of all these tiers and fees, Sacramento Mobile EV Charging offers a massive, undeniable safety net for the consumer. A zero-risk guarantee.
This is huge for them.
The operational manual states unequivocally,
Yeah.
if we can't get your EV charged and moving, you pay nothing. Zero risk. That is an incredible statement of confidence in their ability to interface with dozens of different proprietary EV systems.
It is also the ultimate conversion tool.